So welcome. Pleasure to be here. If you want to take notes on the slides, you can use this QR code and download them from Polybox, which you shouldn't be too scared about it. It's an ETH Zurich cloud service, so you could just download it from there, see if it works. Did anyone try already? It works. Okay, excellent. Good. So maybe I know nothing about you, so let's do a little poll. So who is a theorist, or who wants to become a theorist? Okay. Experimentalists? Okay. Both? A little bit? Neither? Okay, good. Who is a grad student? Okay, postdocs? Undergrads? Okay, this gentleman in the back says he's an undergrad. I don't believe him anything. Okay, yeah. Good. And so who's working with superconducting circuits? Okay, everyone's working with superconducting circuits. And this is the advanced track, yeah? So you know everything. Okay, but the audience is still quite diverse, I think, in terms of experience. Yeah, but I guess since you're in the advanced track, you know some of the things. So I would also invite you to ask any questions as we go. Yeah, this is a lecture for you, and you should take as much as you can out of it. So the star of this presentation will be this device here. So I'll talk about a quantum error correction experiment that we did with this device a few years back. And so this should serve as an introduction to quantum error correction with superconducting circuits in the surface code. And so the team that did this work at ETH Zurich is listed here. And we've collaborated with Alexandre Blaise's lab at the University of Sherbrooke in Canada on this, and also with Markus Müller, who's a theorist in quantum error correction at RWTH Aachen in Germany and at the Forschungszentrum Jülich. So one slide that I also like to show should be encouraging for you, no matter at which stage of your career you're currently in. I think quantum information science is a good field to be in. You have excellent prospects to be in research, maybe continue research in a PhD or in a postdoc, work for a startup or a large IT company, or go on for a faculty position somewhere. And I think this is true since some time, and it continues to be true. So there's lots of opportunities for all of you in this field. So I think it's exciting, both in terms of sort of the basic science, and also in terms of the opportunities that you can have working in this field. And I think if you look at what people are doing these days who spend some time with our lab, and this is mostly selected on people who've actually published with us, and there have been many more students in our lab from many more undergraduates, or so we've maybe had somewhere between 300 and 400 students who worked with our lab at various stages of their careers. So maybe I'd like to start out with discussing with you this device here. So this is about a workshop on superconducting quantum devices. And so this is a device with 17 qubits on which you can realize a distance 3 surface code experiment. And one of the things that I usually say on these occasions, even if it's recorded, this is maybe one of the larger chips where you can look at what is on the device, what the designs look like exactly, and try to learn from it. And for many of the more advanced devices that you can see many publications on, the designs are typically not shared, even though this would probably be very instructive to all of you and would probably accelerate progress in the field if this was the case. And so since this is a workshop about you guys thinking about tools for designing such circuits and doing better quantum information science or better quantum computing with superconducting circuits, it's probably exactly these types of questions that you want to think more about. So this one you can look at in any detail you like. It's also in the publication that we've written on this surface code work, which is cited here. And I'll walk you briefly through this device. So there's 17 superconducting transmon style qubits. They're single-ended, so they don't have two floating islands that are connected with each other with a pair of Josephson tunnel junctions, but just one island that is connected to ground through a pair of Josephson tunnel junctions. And this island is shown in yellow here, and there's 17 of them who are laid out in a square lattice. So this is also a kind of a 2D device geometry, or maybe a 2.5D device geometry. So there's some crossovers for some of these lines, but otherwise it's not a flip chip device or so. And so every one of these qubits has an individual microwave frequency drive line. So there's a coplanar waveguide that has a launcher at the edge of the chip, and which reaches out towards the qubit and has an open end near the qubit. So at this open end, it will have an antinode in the electric field, and thus that electric field will couple to the superconducting qubit to drive transitions in it. And so through these pink lines, we can apply short microwave pulses, which are both amplitude and phase control to the qubit to prepare any state that we like. So then every one of these qubits has a flux line. So that's another coplanar waveguide that reaches from the edge of the chip towards the qubit, and it ends near the qubit in the vicinity of the squid that forms the transmon. And when you apply a current pulse or voltage pulse to this green line or so, it will create a current at the shorted end that will create a magnetic field, and this magnetic field will thread the squid loop and change the transition frequency of the transmon qubit. And in the device architecture that we chose here, 2-qubit gates are actually initiated by tuning the qubits into resonance with each other by changing their transition frequency. So then the couplings between neighboring qubits on these square grids are mediated again by coplanar waveguide resonators that are shown in this bluish color here. It's a waveguide whose first resonance frequency is maybe around 20 gigahertz or so. So effectively, the coupling between these neighboring qubits is sort of capacitive in nature. Yeah? So you don't really make use of the fact that the coplanar waveguide here is a microwave frequency resonator. And you see that qubits that are connected through these blue coplanar waveguides, they can interact with each other. You can have a 2-qubit gate that acts between these neighboring qubits. So then every qubit can actually be read out by coupling it non-resonantly to a microwave frequency quarter wave resonator, and the actual readout resonator is shown in red here, and it's shorted at the far end and capacitively coupled to the qubit. And it's actually quite strongly capacitively coupled to the qubit. And the reason for this is because this device is to be used in a quantum error correction, and in quantum error correction, in comparison to most general quantum algorithms, you're required to do mid-circuit measurements. So your measurements are required to be about as fast as your single or 2-qubit gates, so that the measurement doesn't delay or doesn't extend the duration of one of your error correction cycles. While if you were to only read out qubits at the end of your gate sequence, or you in principle could read them out for as long as you like, yeah, because that's really the last step in your algorithm. And so one thing that is also special in this architecture is that the readout resonator has an individual Purcell filter, and the blue structure here is a so-called Purcell filter. It's just another lambda quarter microwave frequency resonator that has roughly the same frequency as the readout resonator and is strongly coupled to it. And this Purcell filter, it avoids the qubit decay that would otherwise occur if a qubit is strongly non-resonantly coupled to a readout resonator. So even though that the qubit is detuned from the readout resonator, it will still somewhat hybridize with the readout resonator, and that kind of the fraction of the hybridized state then has could decay through the readout resonator and limit T1. And one of the ways how to suppress this decay is through these dedicated Purcell filters. And then maybe one of the aspects that is also interesting about this device is, while there's generally relatively little multiplexing, there's some multiplexing on the readout lines. So these dark purple lines are readout feed lines, and you see that there's a bunch of readout resonators coupled to the same feed line, and these readout resonators are frequency division multiplexed. So each qubit gets a readout resonator at a specific frequency, and then if you space out these readout resonators in frequency space, you can essentially simultaneously read out all the qubit states of those qubits that are kind of connected to the same feed line. So here's a zoom in on one of these qubits. Yeah, you recognize all the bits and pieces. So there's the yellow pad is essentially forming the capacitor of the transmon qubit. This capacitor of the transmon qubit is coupled capacitively to these 4 blue microwave frequency coplanar waveguides that couple that qubit to 4 of the neighboring qubits. It's also capacitively coupled to this large capacitor, which creates the coupling into the readout resonator. And there's also some additional capacitance through the 2 Josephson tunnel junctions that are located here where the squid is formed. And what you also see in a little bit more detail is this green microwave line, which is shorted at the end, through which we can induce a flux in the qubit loop. And so here's even one step more. Zoom in, you see the scale bar. So now we've zoomed in a fair bit. So that's also maybe something that I've not mentioned in the beginning. So the device is not that small. The device on the edge is roughly 14 by 14 millimeters in size, so quite large. And even at this scale, the scale bar here is still 10 microns. So the 2 Josephson tunnel junctions are actually in these locations. They are made by overlapping 2 aluminum electrodes with an oxidized barrier in between them. And so here, this is one of the locations of the junctions, and then the other location of the junction. And this area here forms the squid loop. Yeah? By applying magnetic field to this loop here, the magnetic flux will essentially control the total Josephson energy for the 2 junctions, which are coupled in parallel to the ground. And you can control it by essentially generating a current through this wire, which you can do both at DC to tune the transition frequency statically, or at with some bandwidth, maybe up to a gigahertz or so, which allows you to tune the qubit transition frequency on nanosecond timescales. Yeah, so maybe I'll take this opportunity to ask to see if you have any questions about this device. Yes.
I'm not sure if you mentioned this, but what are those transmission line ends that doesn't happen?
Like these things here, or?
Oh,
here. Okay, good. Yeah, this is just some unused ports. So so the mount for this device, which we made, has 48 ports, but we have 17 qubits, which require 17 drive lines, 17 flux lines, plus 2 times 4 lines for doing the readout. Yeah, and the person who's designed this decided to keep this at the edge of the chip as an unused port. Any other questions? Yes.
Those crossings.
Okay, so I wouldn't mention it again because I've said nothing about it so far, but it's a good question. So there's crossings between these coplanar waveguides, as you see here. There's not too many of those, yeah, but some in this quasi 2D architecture. And these crossovers are done with freestanding air bridges. So there's one coplanar waveguide that lies in the base layer, then the other coplanar waveguide approaches that, and then it is essentially crosses over in a so-called air bridge that you fabricate by having a little bit of resistor, and so you have a freestanding metallized a wire that essentially cuts across.
You're connecting the end of there.
Exactly. So and usually when this gets fabricated or so, okay, good. This I also have not said anything about sort of the dark gray area is a silicon substrate. We do our devices on silicon, and the base layer metallization for this device is niobium, and the junctions are made in aluminum and aluminum oxide, and our air bridges are actually aluminum air bridges. They get done, or for some weird mechanical stability reason, it's actually an aluminum titanium aluminum tri-layer air bridge. If that's really necessary, I'm not so sure, but that's something that was developed when we made these devices, and we still do it this way. And so this gets done in a separate photolithography step, and then maybe the height of the kind of the distance between the top of the separation between the crossover and the wire is maybe around 3 microns or so. Any other questions? Yeah, there's like 2 in the back of either one.
All is the same question. Purple line, crosses also the coupling.
Like these ones here? Or,
purple line which crosses
this one here? Okay.
Same comment that you had before.
This one here, they all work in the same way. Sort of the crossovers are all done in the way I've described.
When you're doing the flux biasing, it looks like the ground current would potentially return like through the junctions, which I understand is sort of a way that you can do like an alternative method of doing flux biasing.
Yeah, there's a lot of subtle details about that, and I would be far from claiming that this is ideal. So you can look at a lot of these things, and there's a lot of details. You would want to understand the response both at DC and at RF. You want to make sure that it couples to the right modes and doesn't affect your qubit coherence, for example. And this has been thought of a little bit, but it's not. I mean, I'm far from claiming that this is the ideal way to do it. Yeah, maybe the Google folks have something more to say about it. Maybe they can say more about it, but there's probably more to say about it. Yes. So there's also lots of or there's, for example, when you make your squid asymmetric, sort of with a large and a small junction, this also matters. It matters how your flux line couples into that.
Yeah.
Sure.
What is the width of the oxide in that?
Okay. So the tunnel junction oxide thickness is very small, or it's even hard to measure how large it is. You could nominally you can try to estimate it from the junction area, the critical current density that you get. I don't know. It's on the. I'll probably say something that is wrong. It's kind of on the angstrom or tens of angstrom level, and the barrier is likely not very homogeneous, because if you look sort of microscopically at at the surface of the film, it's kind of still a bit granular, and likely some of the supercurrent through these tunnel junctions actually goes through kind of the parts with the thinnest barriers have the highest currents, and this could also affect the performance of your device. But we've not looked at this this very carefully, and to some degree, it's kind of magic that these aluminum Josephson tunnel junctions work as well as they do. And if you ask, maybe tomorrow for the panel, no, not tomorrow, on Thursday for the panel discussion, you could ask, okay, what are the biggest challenges? And I think one of the big challenges is how to make really good Josephson tunnel junctions and understand the defects in those.
Like, what's like for the sound filters? What's the general capacitance or optimal coupling strength?
Okay, good. That's very detailed. So there's a few papers about that. So we've written papers about both this single readout resonator Purcell filter combination. And that's by Theo Walter. There's Francois Sviadek has a pretty recent paper which discusses that in quite some detail. There's a paper on multiplexing. So I think this is a bit detailed, and designing these well and making sure that you can fabricate them with good quality is a bit of a challenge. But I don't know off of my head these numbers, and I think it's probably a bit of a too specific question. Not because I wouldn't want to tell you what the answer is, but I just don't know, and it's quite detailed. So. Anything else? So I'll not tell you about error correction, I think, in the end. But since this is a device design workshop, this may be good. Yeah. The one with the junction and the. Like these ones here. Yeah. Okay, good. So. Yeah. Yeah, we had. I mean, this is. I think we had two versions of this. We also had the reverse version of that, where the air bridge goes between the two ground planes. And I think the important point is that, like, when the qubit changes states, you have a displacement current, yeah, and the displacement current sort of needs to be able to flow around your qubit, and so you need to make sure that it's kind of connected all the way around, yeah, and in some of our designs, we decided to have this connection in the base layer metallization, and maybe this was driven a little bit by our initial belief in the reliability of this air bridge process. And we have the reverse, yeah, and if your air bridge process works well, I think this should not make a difference. Anything else?
Very quick question. So I see that you have multiplexing.
Yeah.
Is there any reason that you have two readout lines?
Well, we have two. There's four readout lines actually. So I didn't mention it. So there's four, three of which read out 4 qubits and one reads out 5 qubits. Yeah. So this because you don't see the chip is square, so you don't see the top of it. So this one actually goes. So it's essentially in 4 quadrants or so that the qubits get read out. And here the readout lines are not distinguishing between data and auxiliary qubits in for quantum error correction, but they read out the set of qubits that is in proximity to this readout line. And so, for example, I think Google, at least in some of the devices, made a different choice. So they had readout lines passing by auxiliary qubits and by data qubits separately. Good. Final question, and then I should move on so that I say something about error correction.
Mentioned the base layer metal of IOBM,
yeah,
which has transcendental positives and has higher kinetic inductions and it has oxidation. Can you comment on the choice?
Yeah, so I think the main reason why we are still sticking with niobium is if you do everything right, I think the performance is good. I think it's certainly more tricky because of the oxides and other problems. And a nice example that we make use of a lot is you can test niobium at 4.2 Kelvin, so you can do good dipstick measurements. And when we iterate designs, we tend to do that, and it's a good method for us to. It's the TC, yeah. So it has a if the the film has good properties, you maybe have a 9.2 Kelvin TC, so you can measure it in liquid helium quite well. Certainly kind of kinetic inductance variations with film thickness and so on matter. No. Good. All right, let me move on. I'll probably still not going to talk a lot about quantum error correction, possibly, but to get some of the basic ideas around, but it's all my fault. Okay, good. So with superconducting qubits, yeah, you can, I think two main directions are still to try to see how far you can get with using the qubits in this NISQ mode, or so, where you don't try to correct errors and see what you can do. And I think there were many nice examples running small quantum algorithms in an error-corrected mode. But in the end, if you think about solving problems in which you want to have a guarantee that your result is correct for a reasonable sized problem, you'll probably need to deploy quantum error correction. And in quantum error correction, the idea is to try to encode your quantum information rather than in a single qubit in a set of qubits, and try to be clever about how you encode your quantum information in a set of qubits. And correcting quantum errors is more challenging than correcting classical errors. And one way or one reason for why this is more challenging is because there's two different types of errors. There's not only bit flips, things that turn zeros into ones, or ones into zeros, but there's also phase flips. So if you have a superposition state, a 0 plus 1 could turn into a 0 minus 1, or the reverse. So you need to deal with these two types of errors. And at the same time, you have to kind of figure out whether an error has occurred or not without affecting the quantum information stored in your encoded logical qubit state. And so, for example, if you think about a single physical qubit, and imagine that it was in a 0 plus 1 superposition state, and you were to measure it, yeah, then this measurement in itself would collapse that 0 plus 1 superposition with the probability of a half into either 0 or 1. And then you have kind of affected the quantum information stored. And so then you have to come up with other schemes how to deal with that challenge. And there's one, there's sort of a nice concept which relates to storing the logical state of your qubit psi into the physical state of many physical qubits. And so here's a lattice of such physical qubits. So the physical data qubits are shown in red. And in those, the quantum information gets stored, and the green and blue qubits are used for detecting whether there's errors. And so the idea is then that you make use of the symmetry properties, namely the parity of the logical qubit states, so that you could encode your logical state in a physical qubit state with a given parity. And I'll explain a little bit more what that means. And then a change of parity would indicate whether an error has occurred or not. So what is parity? Okay, so parity is, for example, if you had a string of zeros and ones, yeah, an even parity state is a state in which you have an even number of ones, and an odd parity state is a state in which you have an odd number of ones. So say if you had encoded some logical quantum state in an even parity physical qubit state, and if one of your physical qubits would flip from 1 to 0, or that would turn the number of ones from even to odd. And if you decide that you would encode all your logical information only in physical qubit states with even parity, yeah, then a measurement of parity would not distinguish between the logical ground state, the logical excited state, or the logical superposition states, because they would all have even parity. But if one of the qubits would decay, then they would switch from even to odd. Yeah, and this is something that you can detect in a way that doesn't distinguish between the logical states that are stored in this physical qubits. And because it's not only about bit flip errors, but also about phase flip errors, you need to do the same for 0 plus ones and 0 minus ones. So you can do the same parity criterion for saying, okay, you want an even number of 0 plus ones, and if you measure that parity and it stays even, yeah, there was not a single error, and if it changes from even to odd, there was a single error also in this phase flip basis or in the superposition basis. And I'll give some examples about that. And so this concept is known as the surface code, and the surface code has this nice feature that you can think about or that you can analyze. Okay, if you were to encode your logical information in this physical qubit states, you could think about how low the logical error is in dependence of the physical error for any operation on your physical qubits, and the so-called threshold error, which characterizes the qualities of your code. And in the surface code, the logical error in the logical qubit depends as the ratio of the physical error of the physical qubits divided by this threshold error to an exponent that relates to the size of the logical qubit. So this factor d here is called the distance. So what is shown here is a so-called distance 5 surface code qubit. Distance 5 surface code qubit has 5 times 5, a square grid of 5 times 5 physical qubits. So the distance is 5. The total number of physical qubits in which the data is stored is 25. So in that case here, the factor here would be 5 plus 1/2 would be 3. So when your physical error is smaller than your threshold error, yeah, then this prefactor will be smaller than 1, and you exponentiate it by some factor that depends on the distance of your code. And nominally, you could make that logical error as small as you want by just making more qubits. So as soon as your physical error is a little bit smaller than your threshold error, and if you have the capability of making an arbitrarily large number of qubits, yeah, then you would say, okay, good, I'm done, because my logical error can be arbitrarily small, at least in principle. And so I think the challenge that now everyone who really builds fault-tolerant quantum computers has is to really assert that they could build a system with an arbitrary number of physical qubits so that they can make use of this type of relation to make their logical qubit as good as it needs to be for the given algorithm. So if you have a quantum chemistry algorithm, you could, for example, say, I want to determine the ground state energy or the excited state energy of my molecule to a certain accuracy. The chemist will tell you what an interesting accuracy is. You could write down your algorithm, and then you could ask yourself, okay, what is the error that you can tolerate on your logical qubit? You ask your experimentalist in your lab, okay, what is your physical errors? Yeah, and then you can calculate the distance that you need and how many physical qubits you would want. And the nice thing about kind of this concept of surface code or many other error correcting code is that in principle, you could then build such a device with an arbitrarily low logical error. And that's a bit of a simplified view, but essentially that's the challenge. Or so, I mean, maybe that's something that we could discuss in a panel on Thursday as well. Yeah, is like what signifies that you're sort of done or that your experimental effort was successful. And it would be if you can make systems with an arbitrary number of qubits with a physical error that is less than this threshold error. And the surface code, like this kind of arrangement here, has a threshold error that is around a percentage level, and that's reasonably high for codes. Now there's a few codes that have a higher threshold error, and there's also codes that are a bit better at encoding logical qubits into physical qubits. And the other thing is why the surface code is popular with anyone in solid state physics is because it's known how to lay out the qubits in a planar lattice, and still do everything that you need to do on your logical qubits, how to encode single logical qubits, and how to perform gates between neighboring logical qubits. Good. Any questions on the basic concept? And I'll give a few more basic examples. Yes.
We talked about, an algorithm setup, and we've seen if people are doing it with add-ons.
Exactly, yeah.
How do you see connecting multiple types?
Yeah. So, okay, good. This maybe also I should probably not discuss it a lot now. So the nice thing with atoms is you can sort of reconfigure the atom array. And one of the things that it allows is you could bring a atom logical qubit near another atom logical qubit, and then you can do so-called transversal gates, which are gates in which kind of the physical gate between pairs of physical qubits actually create also a logical gate between logical qubits if you apply this physical gate between all pairs of physical qubits that are part of two different logical qubits. And so in this planar lattices, you would need to use, for example, lattice surgery as a method to create entanglement or to run gates between neighboring qubits. And this has a larger overhead and is more constrained. So it's, in some sense, it's harder. And if you talk to a Rydberg atom person, or they will advertise that feature as being nice, yeah. And surely if one could have arbitrary connectivity or so, that's the thing where you say, yeah, that would be nice if I could move my qubits around. We will not move our qubits around. So things are sort of static, but we hope that we can develop large enough patches and get good enough at doing these things that it will work out this way. All right. Good. All right, so I've mentioned to you that you store the logical state in this D by D grid of data qubits, and then there's these X and Z type auxiliary qubits that sit in the plaquettes or so formed by the data qubits, which sit on the vertices of this lattice. And these auxiliary qubits are used to measure the parity of the data qubits on the vertices of this plaquette. And so how do you measure the parity? So you need to figure out whether an even number of these qubits is in one, or if an even number of the qubits is in an even superposition state, 0 plus 1. And so the way how you could measure the parity on such a plaquette, which corresponds to measuring the product of 4 sort of local Z operators of the data qubits that sit on the vertices of this plaquette, is you could do it in, so building a measurement apparatus that directly measures this. Yeah, you could, if you're a theorist, you could think about what you would need to do that. But you can do a gate-based, an auxiliary qubit-based measurement of this operator here. And the way how to do this is you take the 4 data qubits on the vertices of this plaquette here, and you run C0 gates between each one of these data qubits and an auxiliary qubit that sits in the center. And these gray bars here indicate the connectivity. So now you could imagine like every C0 swaps the state of the auxiliary qubit if the control qubit is in the state 1, and it does nothing when the control qubit is in state 0. So now you can easily see if there's an even number of data qubits which are in state 1, you will swap the auxiliary qubit an even number of times. Yeah, and if you swap it an even number of times, it's essentially as doing nothing. Yeah, so you swap it no time, then it's still in the original state. You swap it twice, it's in the original state. You swap it 4 times, it's still in the original state, at least ideally. So now if one of the data qubits goes from 0 to 1 or so, then you swap it an odd number of times, and then your auxiliary qubit will swap state, and that's something that you can detect. And if all of your logical information is in even parity states, yeah, then this will learn nothing about the stored state. Okay, and then the same thing you need to do in the X basis, so in the superposition basis. And you essentially do the same thing with the blue auxiliary qubits, and you essentially just measure the data qubits in a basis that is rotated by 90 degrees. So rather than measuring it in the Z basis, yeah, I say you measure it in the X basis in the same way. And this essentially tests for the parity in the superposition space. Okay, and so in a surface code, yeah, so you see there's lots of auxiliary qubits, and in sort of one round of the surface code, you essentially need to measure all these auxiliary qubit states after they have run through this gate sequence here. And for that to have any chance of working well, yeah, like all the ingredients need to be good. Yeah, like the single qubit gates need to be good, the 2 qubit gates need to be good, your single qubit readout needs to be good. Yeah? And one of the things is that is interesting in the surface code is that even with, say, a moderately good fidelity or a small enough error on any of these operations, you can still overall win. Yeah, you can, even though that you have faulty ingredients, yeah, you can make the whole thing pan out that you win in the end, that your logical error gets smaller than your physical error. And for example, when we did this for the first time in our lab, I think it was even though that you can of course believe the theorists and read the paper and say yes, this should work, yeah. But if you see it work for real on your own device, I think that's kind of nice to see. All right, so here's a mini example. So this is a distance 2 surface code with 4 data qubits, 3 auxiliary qubits, 1 so-called weight 4 X stabilizer, and 2 weight 2 Z stabilizers. And these stabilizers are essentially realized. These stabilizer measurements are realized in this by applying these C0 gates on the plaquettes in the way that I've explained to you. And so one of the ways how to look at this is that that all these stabilizers commute with each other, and if these operators commute with each other, it also means that they have common eigenstates. And so here's a few examples of common eigenstates, and to see this parity, to drive this parity argument home. So for this surface code qubit here, which is distance 2, the logical 0 could be realized as this superposition of all zeros plus all ones. Yeah, you look at it, clearly it has an even number of ones, yeah, and it also has an even number of pluses, yeah, so this is an even parity state. So then you could look at the logical 1, and the logical 1 is written down explicitly here. It also has an even number of zeros, an even number of ones, and also an even number of pluses, so it's also an even state. And so now you could ask yourself, okay, how do you go from the logical 0 to the logical 1? And you can do so by applying a logical operator to your logical qubit. And the logical operator is just a string of local Pauli operators. So here, this vertical line indicates that a logical X operation on your logical qubit corresponds to a physical qubit X operator on D1, a physical qubit X operator on D4. And if you would do this on this state here, it would create the excited state. So this is a logical X operator. So the operator that swaps your logical state, and it's it has 2 operators, yeah, and it's also so this also relates to the fact that this qubit is of distance 2. Yeah, so the operator that would swap or change the state would have a number of Pauli operators that corresponds to the distance. And so then the logical superposition state is just the superposition of 0L and plus 1L, and for the same reason, it's even parity. And then you can apply the logical Z operator to it, which is this string of Z operators on D1 and D2. And if you do this explicitly, you will see that it swaps the phase on 2 of these terms in your sum here. And so you look at this, yeah, and you realize, okay, everything is even parity in the X and then the Z basis. So this is your logical states. And now if anything flips, either a plus to a minus or 1 to a 0, yeah, you will detect it by just measuring your auxiliary qubits after they've performed these stabilizer operations. Good. And all right, so but maybe one thing that I should have said. So this distance 2 surface code, sort of interestingly, it can detect whether errors have occurred, but this code is too small to actually correct for errors because it can't really identify from the stabilizer measurements where the error has occurred, or what you should correct to return back to the non-faulty state of your logical qubit. And the first code distance that can achieve that is a so-called distance 3 surface code. That's also why we did this experiment on that. And this distance 3 surface code has this 3 by 3 data qubit array. The logical qubit operators are listed here. So it's again this string of vertical Pauli operators and a string of horizontal Pauli operators in the Z and in the X basis. The number of errors that can be corrected in this distance 3 surface code is d minus 1/2. This equation here holds for any distance. So if d is 3, you can correct an error. You can correct any single error that might occur on any of the qubits, on any of the data qubits, or any of the auxiliary qubits. It also can correct some errors that might occur on multiple qubits, but it can correct all of the possible 2-qubit errors. So this code will fail if simultaneously errors occur on 2 qubits. And so if you want to correct for more errors, you need to have a larger distance surface code. For example, if your distance was 5, yeah, then you could correct 2 simultaneous errors. Okay, so then if you count your auxiliary qubits, which do these parity measurements, you always find out that the number of auxiliary qubits is d squared minus 1. So when you wonder, okay, these logical qubits, they come up with these weird qubit numbers. Yeah, there's kind of 17 or 49. You wonder, okay, why is it that? It's typically it's d squared data qubits and d squared minus 1 auxiliary qubits. And these d squared minus 1 auxiliary qubits are used to sort of measure out these other degrees of freedom that your surface code has, so that there's exactly 1 degree of freedom left in the end, and that's your logical qubit degree of freedom. So and by, as I mentioned before, yeah, by measuring these stabilizers or measuring the parity in these different bases, yeah, you can detect whether bit flip or phase flip errors occur. And so in this device here, you see you have 4 weight 4 stabilizers, 2 of the in the X basis, 2 in the Z basis, and then there's also 4 weight 2 stabilizers at the boundary of this code. And the stabilizers are exactly, or are written down down here. Okay, and and then we try to implement this distance 3 surface code on this device here, and maybe you see it a little bit, and I've not mentioned it in the beginning. So now you see this kind of the square letters, and you also see the qubits that are in the center of the plaquettes are the auxiliary qubits, and there are some auxiliary qubits that sit at the boundary and are weight 2, and the one that sit at the center of the plaquettes are all weight 4. So and that's why the device looked like that. Good. So here's a picture of what this looks like. So this is in a package that we designed for this. So this has these 48 ports, yeah, and there's now a few ports are unused, yeah, and that was the question that was asked in the beginning. Yeah, and if you hold this thing into the light in the right way, you see even some of the structures on your on your chip like that. So I think like this week I saw an interesting comment somewhere somebody posted this picture on I don't know what, LinkedIn or X or something like that, and said, hey, this looks almost like this thing that these guys did 20 years ago at Yale, and this is sort of not that wrong or so. Yeah, like I think we at Yale we used these connectors already, and we had a version with when the first circuit QED experiment was done ever. There was a PC board like that, maybe a little bit less fancy, with 2 connectors on it, but it was the same type of connector, and in some sense the same architecture. Yeah. So sometimes things take some time, but it still looks cool, so I like it. So then you put this into a nice sample package, try to screen it well. You put this into your cryostat, so it sits somewhere here, and you make sure that your grad students and your postdocs are nicely dressed up when the photographer comes around. So, and then you close your cryostat, and you have some electronics, and sort of this is one of our newer setups with the electronics for running such a distance 3 surface code. So you see that there is some room for some more electronics, and currently in this setup we are doing some of these lattice surgery experiments with extra electronics. Okay, and then these things never happen on the spot. Yeah, if you look at, okay, how did repeated quantum error correction develop, or there were really many steps from detecting single types of errors, either bit flips or phase flips, from doing a single cycle experiment where you detect both bit and phase flips, but only once, to experiments where you repeat the error detection, but only in a too small code, at a too small code distance. And at some stage, everyone was ready to do repeated quantum error correction in codes of sizes that allowed for correcting for these errors. And our experiment was one of one of the first one that achieved to do that with superconducting circuits. Good. Okay, good. So maybe I'll not go through this slide in much detail. So in superconducting circuits, or in most architectures, there's no direct way to do C0 gates. Yeah, so there's not the physical interaction that implements the C0 directly. Typically doesn't exist. And so in our devices, we do so-called C-phase gates. And so to turn these C-phase gates into C0s, we apply additional single qubit gates to do these parity measurements. But the function they fulfill is the one that I've explained. And then one of the first things that we tried is do these parity measurements work? And so here's an example for such a plaquette here with 4 data qubits and an auxiliary qubit in the center. And so to test whether your parity measurements work or your stabilizer measurements work, you just go through your data qubit states from all zeros to all ones, yeah, and you just run your circuit, and you see whether it tells you correctly whether you were in an even or an odd parity state. Yeah? And as you can verify for yourself, it does so successfully in the cases that are indicated here. And you can also check how well it does by looking at the error. And the error on this weight 4 stabilizer measurement was maybe around 7%. And when we simulated, it was sort of similar. And then you do this on all your stabilizers, or there's 8 stabilizers for weight 2, for weight 4. And you see whether this works. Yeah? And then if you stare at this a little bit and analyze it a bit, you can see that it works reasonably well. The small stabilizers have a little bit smaller error. The weight 2 stabilizers have a little bit of a smaller error, and the weight 4 stabilizers have a little bit of a larger error. And then when you see that, you can then think of, okay, good, if I now put this together, I have a chance of maybe making my surface code implementation work. Yeah? And what I find sort of, and that these errors are on the scale is maybe not so surprising, because in the end you have 4 2-qubit gates, you have a couple of single qubit gates, you have your readout, everything is a little bit faulty. And the errors accumulate, and despite the fact that the errors accumulate in the surface code, yeah, you can suppress the logical error if your physical errors are small enough. And maybe for clarity, in this particular device, the physical errors were near the threshold, but not below the threshold. Yeah? And now the newer Google work sort of nicely demonstrated that the physical errors can actually be below the threshold. And one of the ways to demonstrate that is by increasing the distance of your code from 3 to 5 to 7. And what that should do is you should see your logical error decrease exponentially. And that's what Google was able to show. And that's probably going to be presented in one of the lectures later this week. Okay, so here's the gate sequence. So there's this 17 qubits, 9 data qubits, 8 auxiliary qubits. And in our gate sequence, we ran the 4 Z stabilizers first, and then the 4 X stabilizers second. And actually, maybe a special aspect of our experiment was that we, after the coherent part of the stabilizers did execute on one type of stabilizers, we read out those auxiliary qubits, and we do the reverse with the other auxiliary qubits. And that allows us for the cycle to be around 1 microsecond. Yeah. And here you also see now if your auxiliary qubit readout was much longer than your gate sequence, or that would extend the duration of your cycle, and that would reduce the performance of your surface code. Good. So the cycle duration is about 1 microsecond. And in the first cycle, you essentially can prepare these logical states, the logical 0 and the logical superposition states. And sort of for our own lab, okay, this was maybe one of the larger circuits that we ran at the time. So this includes like maybe 800 single qubit gates and about 400 2-qubit gates when you repeat this maybe up to 15 times in this particular experiment. So that took some work for us to get things pushed into that direction. Good. I think we're sort of out of time at this point. And now I have to see what I would do. So I've not maybe I get out of this presentation mode. Where's my mouse? Here's my mouse. I will not stop sharing, so I need to move this somewhere else. Slideshow. Why can't, okay, this thing. It's all good. Yeah, I'll probably mess up your schedule, but I'll take the free. Yeah.
You can go like 5 minutes.
Sure. I'm just trying to switch this thing to. Where the heck is the presenter mode? Use timings. I can't switch it.
Okay, sorry. Okay, sorry.
No, I want to so that I can. Okay, maybe I'll do this manually. Sorry for the little interruption. I hope that was smoother. I should probably have just clicked forward. Okay, so then what you essentially in the end do is you initialize your logical qubit in the 0, in the 1, or in a superposition state. You run your gate sequence as I'd shown, and at the end of n repetitions of this gate sequence, you read out your logical operators, which were this string of physical qubit operators for z and x vertically and horizontally, and you calculate their expectation value using the information of the auxiliary qubits that indicate whether an error has occurred or not. And if an error has occurred, you're trying to identify using a decoder what that error signature, the so-called syndrome, tells you how you should correct your logical qubit state. And when you have done that, you can use that information in your measurement of the expectation value of the logical operator. And that's what is shown here. So what is shown here is the logical Z operator expectation value for 0 and 1 logical, and the logical X operator for plus and minus logical. And it's plotted versus the number of repetitions of the error correction cycle. And on top, you see what that means in time. Yeah, it's in multiples of this 1 microsecond. And what you do see is then, of course, that also the logical Z operator and the logical X operator, they decay with time, despite the fact that that you run your error correction code. Yeah, the error correction code will never work perfectly, so your logical qubit will still decay on some time scale, and what that time scale is reflects on what the ratio between your threshold error and the physical error is in this particular device. So what we see here is that the logical lifetime was about 16 microseconds, and the logical coherence time was about 18 microseconds for this particular device. And you could then simulate it and find that the simulated results were sort of similar to the experimental ones. And in particular, you could then analyze what is the logical error probability per cycle. So you remember in the very beginning, I mentioned this quantity epsilon L, which you want to get as small as possible. And here the logical error is plotted versus cycle. And so it increases exponentially with time because of this T1 and T2 effects in the logical observables as well. And from this, you can extract the logical error per cycle, which for this particular experiment was about 3%. Yeah? So you have a 3% logical error per cycle, despite the fact that all your stabilizer measurements have either 8 or 4% error. Yeah? And okay, so how well does this do? So this is now has some of the newer Google data on it already. So for the early experiments, sort of our superconducting circuit experiment was the first one that was able to do the full quantum error correction in the surface code in a repeated fashion. Yeah, and it had a 3% error. And and it had sort of a largish repetition rate of about a megahertz, so a cycle time of about 1 microsecond. So there's this nice work with ions, and maybe one of the distinguishing features of this early ion work was that the cycle times are much slower. And you could then, in the end, if you compare architectures or so, then wall clock time at some point might also matter, while maybe currently it's not quite there yet. And so here's some newer work also from Google in surface code and also in the color code, and there are some additional points here. And sometimes there's a little extra panel here which plots the number of co-authors on the paper versus the number of qubits on the device. So, and you could do that plot as your homework, for example. Okay, so these are two of the quality criteria, and we've tried to analyze, and I'll not discuss it in detail, how close our experiment was to this threshold error. And it was reasonably close, so it was not a factor of 10 away from this threshold. But it was also certainly not better than the threshold, and we think that through analysis, we were about a factor of 2 away from this threshold. And of course, we couldn't do this nice experiment that Google then has done by just scaling the distance, yeah? Because for that, you need to have many more qubits on your device and everything to work out. And so here's the just scaled the distance version, yeah, with 3, 5, and 7. And then you can, like, this is essentially the equivalent of the plots that I've shown to you before, where you look at how the logical error increases with cycle or cycle number or cycle time. And then if you plot that logical error per cycle versus distance, on a log scale, you see this exponential scaling, which is what you want, yeah, which is what was advertised for the surface code. Good. So I told you about this device, which we're pretty happy with, and is nice to look at, and you should enjoy that you can look at it rather than not being able to look at it. So this we've done on that a few years back now, the full distance 3 error correction, and seen that it's close to threshold. And so currently we're working on realizing gates between logical qubits. And so we have devices, and of course, many others are working on this, and there's also quite some results on this already. When you have 2 logical qubits sitting next to each other, you can actually perform logical operations between the logical qubits by performing lattice surgery. So this is operations that at the interface between 2 patches of surface codes do special operations both on possibly additional data qubits and on the stabilizers at the interface between 2 surface codes to essentially effectively entangle neighboring logical qubits with each other. And so if you're curious about that, sort of, we have like a first version of that experiment in this paper here on the archive. And with that, I'd like to thank the current team at ETH. I mentioned to you, having a good team is really essential for this. And this picture we took last week. And if you're curious at some stage, we're always looking for people to work with us. So thanks a lot. Sorry for going a bit over, and maybe we still have time for a couple of questions.
There's time for 2 questions.
The undergraduate student, or maybe should leave someone else. Go for it.
Curious how much you thought about the crossover when the logical qubits might overtake some of their counterparts. Start to think about being able to do like 100 plus physical. Right now we can do some like Trotter evolution on qubits with 5,000 gates, 2 qubit gates, and arbitrary 2 qubit location. And in the QEC regime, I just wonder how much what you're thinking around that kind of crossover when it's beyond just memory. You also have to do 2 qubit logical operations. It's a long distance question. When you take into account the gate cost, T gates, and
so whether Yeah, so I think this touched only on one corner of this quantum error correction question, and essentially how to keep an encoded logical state in good shape. And it said nothing or very little, like this talk said nothing about how you would do gates between logical qubits, and how you go about doing these non-Clifford gates in logical qubits, which are difficult questions, which then have to do with realizing like T gates or your fractional rotations of the logical qubit state. And there, of course, there's lots of theory work on that, how you could distill those operations that we're currently missing. I'm not sure whether I have a super deep insight on the ways how we would tackle those questions in our own lab at the current stage. We tend to do experimentally motivated work, yeah, and it's maybe a thing that I like doing, and that I think I have some good insights in, and so I personally I don't spend a lot of time on thinking about how I would distill T gates or so in these devices, because I know this is still a bit away for what we could do. And maybe that's a flaw or a feature. I don't know. I have not a lot to say about it at this stage. It's going to be very challenging. If you want to have a general statement on it, I think there's some progress. And if you look at where you would need to be in the future and where we are now, there's still a huge gap. And so there's lots of room for doing better work. So for all of you, you can contribute to tackling all these big challenges. And so it's not for tomorrow that you have a fully fault-tolerant, error-corrected quantum computer in any of the labs. I think almost even with any amount of money currently. I think it's all about having good people who think about it, who come up with good solutions, who continue the development of these devices, make them much better. For example, one thing that would help a lot, if you could make all the physical qubits 100 times better together with their gates, yeah, this would be much, much better. Then you would need less overhead for the logical qubits, and this would make it much more feasible. But if you, like maybe conceptually, you could think about what you would need to make things 100 times better on the physical level. But honestly, I think no one knows what it is that will really get us there. Good.
All right, cool. I think that's all the time we have for questions. So we can thank our speaker.